I'm Hortensia Soto, MAA President. I hope you all have been enjoying MathFest. Yes, thank you. Yes, that's the response I wanted. So let's see. I have the great pleasure this morning of introducing Dr. Mary Lou Zeeman, who's going to present her first of 2 lectures as part of the MAA Earle, Raymond, Hedrick lecture series. And if you've read anything about her, you know that she has a prestigious academic background with degrees from Oxford and Berkeley. She's held positions at the Institute for Mathematics and its Applications, at MIT, at the University of Texas San Antonio, at the University of Michigan, at Cornell, and now she's at Bowdoin College, and she started that position in 2007. She's also the co-founder and co-director for the Mathematics and Climate Research Network. She's a co-founder and deputy director for the Institute for Computational Sustainability. She's on the executive committee of the Computational Sustainability Network, and she's part of the core leadership team for mathematics of planet Earth. She has delivered numerous presentations, and in fact, in preparation for this introduction, I watched one of her videos when she presented at the National Math Festival. I was impressed with how she made mathematics accessible using examples such as fishing from a kayak. As I started digging around a bit more, I found a few nuggets that I want to share with you so that you get a sense of the person behind the researcher. This part I feel like I must share. Her research that she's going to be talking about really stemmed from a conversation with a gynecologist. This is where you laugh, because I found that funny. But her research is accessible to undergraduates, and she and her colleagues work to empower students and scientists to use mathematics to find solutions to complex environmental issues facing the Earth today. And I found a quote that I really spoke to me, and I think it speaks to her work. And she says, "The point of education is not to make the lives easier for those who happen to be able to get educated. It is to train them to use the talent they were given for the common good." So sit back and learn how Dr. Zeeman uses her research for the common good. Please help me in welcoming Dr. Zeeman. Thank you.
Thank you. Hello. Thank you, Hortensia, for that lovely introduction. And we'll just get this working.
Please have to sign in, because I'm also going to know what to sleep. There we go.
That last quote about education for the common good is actually what Bowdoin is based on. Bowdoin has a Center for the Common Good. The whole environment at the college is based on education for the common good. I'm so lucky to be there, to be at an institution that has that core. And Hortensia was right. The research I'm doing now did really originally stem from a conversation with a gynecologist. At that point, it was to help that gynecologist, who was an infertility specialist, understand some of his own results. And so I'm not going to be talking about the gynecological results today, but it was doing that work and having him change his treatment as a result of what we did. We did a bunch of math and stat, and he changed the way he was treating his patients and got a higher success rate. And that really blew my mind. It's like, oh, I can be useful. I can be somebody who loves math, loves doing math, loves the beauty of math, and apply it to things I really care about. What do I really, really, really care about? And women's health was one of those things, but even more urgent than women's health was the planet, the state of the planet. And so that is what inspired me to start working on questions that were to do with the health of the planet. And a bunch of rabble-rousing, so that a lot of us mathematicians could liberate ourselves to work on things to do with the health of the planet if we wanted. So, okay, today I'm going to talk about Flowkick systems for studying resilience. This is joint work with a lot of people. Here are the major players, a lot of junior colleagues that I really enjoy working with. and Nina Fethman, who is not a junior college, she's perfectly senior. And our plan today is we'll talk a little bit about sustainability and climate, just to get in the mindset, and then about resilience. What is it? What do we mean by that? Why do I think Flowkick systems are useful for studying some aspects of resilience? A few applications to get a sense of it, and then stability questions, which would lead into tomorrow's talk. I talk again tomorrow morning. And that talk has quite a different flavor, but follows from the questions that were raised in this talk. So, okay, sustainability. Just in case you've never thought about it, the United Nations, which consists of almost every country in the world, has 17 sustainability goals that it sets out, and that's how they measure the health of the planet. Of these 17 goals, number 13 is climate action. It's just one of 17 goals. The United Nations collaborated with the World Meteorological Organization to create the Intergovernmental Panel on Climate Change. And the mandate of this panel is to summarize the published scientific literature on climate change and its impacts. And the point is to make the scientific literature, at least at some level, accessible to the decision makers and the governments who are supposed to act on this for us. And to the rest of us. We can all read their reports. They're very dense, but the point is that's the summary, not of the media, but of the scientifically published literature. But, you know, we hear the message is changing. It's gone from being described as climate change to climate disruption to a climate emergency, now to a climate crisis. And just in the last couple of weeks, we've had these kind of headlines. Here in Florida, you know, the water's hotter than it's ever been anywhere in the world. This is also from July, a few weeks ago, were the hottest global average temperatures over the planet ever recorded. And this came out a week ago, that the data suggests, perhaps, according to a very interesting paper that's a combination of dynamical systems and statistics and data, that the potential for collapse of the Atlantic overturning circulation is closer than we would like to believe, as in this century. So there's a lot of fear, right? I mean, it is a very frightening thing, this climate change that we're creating. So I wanted to share this diagram from an IPCC report, because I find this diagram really inspiring and helpful for thinking about what should we do if we're mathematicians, if our talent is mathematics, what should we do with it? So this is a chart that lists down the side here all the sustainability goals of the United Nations, except number 13 is not there. Remember, 13 was climate action, because this is all about climate action. What are some things we can do for climate action? One is we can green our energy supply, or we can reduce our energy demand, or we can change our land use, and it's kind of related. And this is a graph of the trade-offs and synergies. Things marked in brown are trade-offs, meaning if you do the climate action, there's a trade-off with the other sustainability goal. And things marked in blue are synergies, meaning if you do the climate action, that can synergize with improving the other, working also towards the other sustainability goal. And the length of these little boxes represents the strength of the connection, and the shade represents our level of confidence in that assertion that there's a synergy or a trade-off. And what I like about this chart is there's a lot more blue than brown. We hear a lot about the trade-offs, about how we can't make climate action because of all the trade-offs against all the other good things we'd like to do. But there's a lot more blue than brown. There's a lot more synergy between having climate action and a healthy planet than trade-off. And that I just find really inspiring, and to think, okay, whatever it is that we happen to care about, we're mathematicians with a social conscience, wherever we choose to put that social conscience, any of these sustainability goals, it can work in synergy with our climate crisis, with action to help with our climate crisis. So that's just kind of the main message. But now let's move into some detail. So what aspect of all these questions all the climate questions that I was observing, what aspect did I find interesting? And it was exciting from a math point of view, and it was this one. Resilience, this idea of the ability of a system to absorb change and disturbance while maintaining its basic structure and function. And you talk to people in any discipline, they all have a sense of what resilience means. It's like a quick anchor for communication across the disciplines. And if you like the idea, I found this book very nice for understanding resilience in a few different ecological examples. But as soon as you really start talking to people, and especially if you want to build a math model, then you need to get a bit more concrete than the qualitative idea, and you need to know resilience of what to what. So let's just underline those. Of what? Resilience of the basic structure and function of the system. To what? To the change and disturbance it might be subjected to. So we're passing that little qualitative sentence into 3 different ideas here. And so first let's think about possible disturbance patterns. One could be the kind of city disturbed by some disaster, and that would be a large disturbance, a single isolated large disturbance. Or we could think about the corals and how they're suffering because of gradual ocean acidification, so the ocean gradually gets more and more acidic. And that would be what's called a press disturbance, a continuous press disturbance. Or it could be the continuous chatter of ongoing weather variability. Or there could be all kinds of these different types of disturbances mixed together. So there are many different ways that a system can be disturbed. The ones that we'll focus on today are regular repeated disturbances. So those happen if we're managing a system, for example, if we're harvesting a system, or if we're trying to control invasives, and I'm sure you can think of many other examples. They also happen, for example, in fires, forest fires, savanna fires. They happen in immunology, when there's an epidemic going around and we're repeatedly being re-exposed to the virus through our friends and neighbors. So this is what we're going to call a flow-kick system, a system which flows for a time between disturbance events, and then the disturbance is a kick. And we'll set up a math model of that. And there are many ways to set this up. We'll just look at one of them. But before we go there, let's just compare this with, in case you are familiar with a bunch of existing resilience indicators or can think of some ways of measuring resilience. Let's start with a one-dimensional dynamical system. So that just means things can move along this line, and as shown here, there's an attractor. So if you're either side of the attractor, you get swept towards it. But there's a basin of attraction. Outside that basin, you go somewhere else. But anywhere inside this basin of attraction, you come to the attractor. You could also view this function, this system, as having a potential function, if you're a physicsy frame of mind. So you think of that potential function is a landscape, and there's a little ball that can roll on the landscape, and it's going to, as if it were rolling through molasses, slowly get down to the minimum. It's going to stay there. So one way of measuring resilience would be to say, well, what's the size of the basin? And that would be telling you the resilience to a single isolated disturbance, because if you give a kick larger than the size of the basin, you will kick outside that basin and you're gone to whatever other attractor. Or another way of measuring resilience could be to look at the eigenvalues of the linearization of the system, which is a way of saying if you disturb a little bit away from that equilibrium, how slowly or quickly will you return to equilibrium? So it's a very different concept, but it's the same idea of what's the response to disturbance. It's just about little local disturbances rather than large ones. We're interested in this idea, the steepness, which is controlling the balance between a disturbance and the transient dynamics. So if you flow for a little while, suppose you are at the top of this suppose you're a ball at the top of this green band, and you flow for a little while, you're flowing towards the attractor, but then you get kicked up again. And then you flow for a little while, but then you get kicked up again. And then you flow for a little while, and you get kicked up again. So you see that there could be some kind of region of flow kick stability up there. And it depends on the steepness, among other things, of that basin. This is not the same thing as what you may be familiar with, the whole idea of stochastic differential equations, and then what happens is if you have a stochastic differential equation which is subject to white noise at random disturbance times, the noise can accumulate so fast that you are guaranteed to escape the basin. And so the questions become, when will you escape? What's the estimated escape time? That's not what we're doing, because we're bounding we're bounding the flow time away from zero, and we're bounding the disturbance size. So we really can stay in the basin, we don't have to escape. Okay, so let's define a flow kick system. So we'll move up to two-dimensional dynamics just to define the system. So here, starting with a system of ODEs in the plane. This one happens to be a linear example. It doesn't really matter what the example is, but I wrote it there so that we'd have something to hook our ideas onto. So at every point in the plane, like if you do some point up here, then f of x shows you your direction of motion. And if that differential equation is saying you've got to follow f of x everywhere, then these solution curves, these curves are the solution curves, and they're showing you where you're forced to flow under the dynamics defined by this vector field. So the flow, phi sub t, we're going to use this a lot. The flow phi is the set of all the solution curves that are just moving according to the dynamics prescribed by f. So we're going to focus in on that little box, and we're going to create a flow kick system. So we're going to choose a flow time. So if we start at some point in this little box, we'll flow just for that flow time. And then we're going to we're going to define a kick vector. So here we go, we're in the box. We've started out here. We've chosen this flow time, and then we're kicking up. So that's just an example. We chose a tau, we chose a vertical vector, and we're defining our Flowkick Map, which we're calling g tau k, and it just means flow for the flow time and kick. And then we iterate it. So we flow and kick and flow and kick and flow and kick. And it's a special case of impulsive differential equations, but sufficiently special to be nice to think about independently. So we keep on iterating, and eventually we land at some equilibrium of this flow kick system. And this equilibrium really makes us think about that balance I was just talking about of the transient dynamics, like rolling down the hill, and the kick pushing you back up the hill. So the transient dynamics of flowing wherever you flow on the flow, and then the kick kicking you back to where you started. So it's interesting that systems under disturbance, regular disturbance, force us to think about transient dynamics, not just the asymptotic dynamics of attractors. We need to know the dynamics all over the place. And our flow kick system's actually a map. So even though we're thinking flow kick, we're actually just seeing, I've just graphed there the ends of each flow kick. So those little dots are what happen after a flow kick map. So here what I'm graphing is started at several different initial conditions around this plane, and graphed their flow kick equilibria, their flow kick trajectories. So the dotted curves are their flow kick trajectories. And it's all superimposed on the underlying differential equation and that underlying flow that we had before. And so one thing you'll notice is it appears that, and it is true, it's a theorem, if we start with a linear system which has a unique equilibrium in the underlying flow, then the flow kick system will also have a unique equilibrium, and the dynamics of that unique equilibrium will just be the translated time tau dynamics of the original underlying flow here, this underlying flow. So whatever was going on there, it's just a discrete version of it going on up here. So it's very simple, it's very neat, and simple, neat things tend to happen with linear differential equations. So a useful observation to make also is that we can put that equilibrium, that unique equilibrium, we can put it anywhere in space. Because once you decide where you'd like to put it in space, so we want to put it here, choose that point, flow for as long as we want, and then kick back to that point. There, we've made an equilibrium where we wanted. We chose a flow time and a kick to put the equilibrium where we wanted. So we can put it anywhere, we can put it over here, we can put it wherever we like. And that observation, that little explanation of why we can put the equilibrium anywhere we like, was not dependent on it being linear. So for a nonlinear system, you can also put the Flowkick equilibrium anywhere in space, anywhere in your state space, which is, again, brings our attention to the transient dynamics going on in that state space. And we have to start asking ourselves, okay, which regions of state space are desirable in our application? And which regions of state space are undesirable? And those those human values that we associate to different parts of state space become even more important. Why are the flow dynamics just translated to the equilibrium? So here's the proof, it's very short. Remember, the Flowkick map was the flow plus a kick. So if we differentiate the map, that's the total spatial derivative. Differentiation is linear, so it's the sum of the derivatives. The kick is constant in our formulation, and therefore the derivative of the kick is 0. So it's the total derivative of the flow. The flow is from a linear differential equation, and so the total derivative of the flow anywhere is the same as at the origin. So that's why, for a linear system, we're just translating the local dynamics at the underlying equilibrium to the Flowkick equilibrium. But of course, that line is not true for nonlinear systems. So let's look at some nonlinear examples. Here's a Lotka-Volterra competition model. So it could be modeling two competing species. There are very many examples of competing species. We might think about different kelp in the ocean. That's becoming an issue in the kelp forests. With competition, with this example of competition, each species can drive the other to extinction. That's represented by these sinks on the axes. The equilibrium in the positive cone is a saddle, which means it's unstable, so there's no stable coexistent state. We won't see both these species together, we'd see one or the other. Now remember what we do for Flowkick. We flow and kick, and we iterate, and that brings our attention to those transient dynamics balancing the kick. So let's do it here. Here we've chosen an example of a flow time and a kick, and that kick is slightly in the positive, into the positive cone, so positive in both directions. And we see, it looks like an echo of the big system, of the original system, just sort of translated into the positive cone a bit. But if we choose a slightly different, bigger kick, then we get a completely different looking system. The Flowkick system has a sink, an interior sink with coexistence of the species. So that tells us that there are Flowkick bifurcations, of course, and a whole world of Flowkick bifurcations to study. So now let's turn our attention to a few applications. So this is, I'm just going to mention this paper because we've said that there are Flowkick bifurcations. So Alana and Sarah have written a very nice paper about fire disturbance in savanna models. So that's a question of, do they become all grassy? Do they become covered in trees? Do they have a balance? And so they've done a Flowkick bifurcation analysis of a Lotka-Volterra-based model of savanna fires and shown that the Flowkick bifurcations echo and enrich, show more. There are more possible bifurcations for the Flowkick system than for the underlying ordinary differential equation system. So more behaviors are possible when you take into account the Flowkick nature of the application. Now let's look at harvesting. So it will take a very simple example of harvesting, a one-dimensional fishery that a lot of us teach in our classes. But the point of this is I want to focus on the state and dynamics of the system and the property of the system, still teasing apart this statement about resilience. So let's start with a logistic ODE for a fishery. So in case you haven't thought about this recently, what happens over time if we start here at x equals 100? So this is actually a graph of the derivative. So the derivative is 0 here. So that means that it's an equilibrium. There won't be any change. The model population is stable at carrying capacity there. So what happens if we start somewhere here at positive population size below carrying capacity? Again, this is a graph of the derivative. So the derivative is positive here, which means this, the population is increasing, and so it will increase to carrying capacity. These are all things that those of us who teach it, this is deep under our skin, but in case you hadn't seen it recently, I just wanted that to feel solid before we go on to ask, what if we start at carrying capacity and harvest harvest kappa units of fish every tau units of time? So here's one possibility. We harvest, so we reduce the population, then we grow. Reduce, grow, reduce, grow, reduce, grow, and we balance somewhere. It's at a Flowkick equilibrium. Here's another possibility, that we're harvesting too much, and so we don't have time to recover from the amount we harvest between harvests, and so we drive that species to local extinction. And we could ask, what are we talking about here? Resilience of what? So we could describe that as the resilience of the basin of attraction, or the resilience of a stable equilibrium in that basin of attraction. And we could plot these results in the disturbance space. So here we're graphing disturbance space. So this is tau and kappa. This is the flow time that we allow and the kick size that we allow. So this point represents the small kick every time unit. And this is the large kick every time unit. And I've colored green for it was resilient and blue for it was not resilient. And now we're changing the coloring system, because if we did that at every point in space, we get this boundary. Under here, all these choices of disturbance regime allow for an equilibrium with a positive population size. Out here, all these disturbance regimes lead to extinction of the fish, that local fish species. So this resilience boundary is interesting. That's like a bifurcation boundary of something. If you happen to think in terms of one-dimensional dynamics, I've plotted a few more points. You can think about the one-dimensional dynamics having an equilibrium. That's our Flowkick equilibrium here. At the black point, at the green point, there's a Flowkick equilibrium. At the blue point, there's no longer an intersection between our one-dimensional map and the diagonal, so there's no Flowkick equilibrium. But when we move in and allow a longer time between harvests, that changes the shape of this curve and allows a Flowkick equilibrium. So if you're not into 1D maps, that was way too fast. But if you are, you can see how this is a bifurcation curve for the 1D map setup. So let's think about some features of this resilience boundary. How is it useful? So one thing to notice is that here's a disturbance regime to which the fish were resilient. And here's a disturbance regime which is twice the fish half as often. So same total rate of harvesting, but the population is not resilient to that one. So that's something that the discrete nature of this Flowkick approach tells us that is different than a continuous system could tell us. Same disturbance rate, one is resilient, one is not. What else could we think about? For this entire system, we've got this whole system that we were drawing the whole resilience boundary for. This area up here is finite. we could think of that area up there as measuring, as some kind of measure of resilience. It's a bit more sophisticated than just basin boundary. Alternatively, we could think of a particular disturbance regime and say, how far is that from the boundary? How far is it vertically? How far is it horizontally? How far is it area-wise? And those could be ways that we're measuring resilience of a particular harvesting approach to the environment. If disturbance is not usually regular, it's usually stochastic. So one can also prove that if we take a domain that's entirely within this resilience boundary, and we choose to disturb it with stochastic flow times and stochastic kick sizes taken from within this, this domain, then these 2 points bound the behavior for the stochastic system. So it tells us we have the stochastic system's not going to escape, it's not going to be non-resilient. So not only that, we've got bounds on the behavior for the stochastic system. That's not true here. If we tip over the boundary a little bit, the resilience boundary a little bit, but I don't know what happens. We're still thinking about that. It's an open question. Be happy to hear other people's thoughts. Definitely the kind of thing that a good, strong probability theory background would help with. And now let's think about the same example, but from a more management point of view. So here, what is the property of the system that we care about? So we were just talking about the state of the actual system. We were talking about what happened to X before. But now some property of the system. What property do we care about? Do we care about the population size for this fish, the stable population size? Do we care about the yield, how many people we can feed? Do we care about the profit so that we can keep fishing? So we can take that same resilience space. So every one of these R is the same resilience boundary in every case. And what we've mapped back onto this into this resilience space, this tau kappa disturbance space, we've mapped in the contours of the property that we care about. So these are the contours of the equilibrium value of the fish under this Flowkick, under each of these Flowkick disturbance regimes. These are the contours of the yield. These are the contours of the profit. And you see, if you wanted to actually optimize, so let's move down. If you wanted to optimize, you'd be going to different places. So you would say you can't optimize all of them at once. And it's, if you have multiple stakeholders for an ecosystem management, this is perhaps one way that you can pull back everybody's needs and think about, rather than optimizing, satisficing in the world of, that's a large idea in the world of control theory and social science. But it's a space in which to compare the different things we value. Okay, moving on to another example. This is looking in immunology. So here's your immune system. These equations are taken from a very nice paper by Cow and Co. And so what aspect of the immune system have we got here? There's obviously a whole bunch of equations. These four, I need my glasses for this. This is the amount of virus that is in your body. The virus is infecting cells. These are target cells from which we're going to get infected cells. The infected cells produce interferon, which come back and help dampen the virus. So this is all the fast response. This is 10 days. There's a 10-day time scale. These four are the fast response, and it's the spike in virus and spike in interferon and spike in infected cells that we can think of as a proxy for us actually feeling ill. So those represent an illness. This is your slower immune system, the B cells producing antibodies which then linger in your system. And so let's look on the longer time scale. Here's the long time scale. The B cells and antibodies take this, we're still on days, this is now 300 days. And it's not until those reduce back down to low levels that your immunity wanes, and so this is the first moment for this particular setup. This is the first moment at which the little tiny viral load, which stimulated that in the first place, it's tiny, it's so tiny we can't see it. So the little tiny viral load which caused this excitable response, this is the first time that that little tiny viral load can stimulate a second response. So we have this excitable system which has multiple time scales, and in that, as we've said, the immunity eventually wanes and re-exposure to the virus will re-excite the system and we'll get the next round of flu or whatever it is. But if there's a circulating pandemic or epidemic, and we're regularly getting re-exposed to small amounts of virus, then here we are. This is lots and lots of little exposures to small amounts of virus, the same small amount that triggered the first illness. And here we are going on beyond 400 days with no re-exposure, and with no second illness. So remember, in the last slide, you got ill again in less than 300 days. Your immunity had waned in less than 300 days. But here we are going beyond 400 days, and we still have immunity because our immune system just being primed enough. We're not getting big viral loads. We're not getting any of that illness symptoms. But our immune system's just primed enough in a subclinical way, below detection levels, that we preserve our immunity. Except that doesn't always happen. Here's a slightly, very, very slightly bigger kick. Regular kick, and this one can lead to re-excitement. So and this is what is observed in the world of immunology, that sometimes repeat exposures do seem to protect, and sometimes repeat exposures don't. So we can look at this system at least and ask what re-exposure patterns do protect us from illness. And it's a really interesting set of our tau k disturbance space. So just like we were looking at before, tau k disturbance space. Only now we're seeing these threads, which will look familiar to people who have seen this kind of thing within dynamical systems before. But the blue here represents the re-exposure patterns that protect from illness. So one question is, okay, why this interesting shape in this context? And we can ask our question again of what happens if we try stochastic re-exposure patterns from deep within that place where you have protection from illness. And there's a surprise. So here this is a stochastic re-exposure pattern, stochastic kick sizes, stochastic times between them, but all of them drawn from that little supposedly safe triangle where we're protected from, safe rectangle where we're protected from illness. But 77% of these stochastic simulations lead to illness again before 600 days are up. So that was a bit of a surprise, and that's one of our interesting questions that we're working on, and happy to have ideas. How does that work? But it shows again there's real mathematical richness in this very, very simple concept, which is representing one of the simplest ways of thinking about resilience to repeated disturbance. And resilience to repeated disturbance is what most ecosystems and most human systems exist in. So finally, for the last couple of minutes, I'd just like to talk about stability of Flowkick Equilibria, to give you a hint of a taste of what we'll talk about tomorrow. So here's a different example of a Flowkick system. It's one of those two-dimensional Lotka-Volterras again. Here's a Flowkick equilibrium where we flow and kick back. So x1 is that Flowkick equilibrium. How would we try to figure out, how could we compute the stability of that equilibrium? If it was just a simple an ordinary continuous differential equation, we'd calculate the eigenvalues of the Jacobian and we'd be done. It would be great. But here, the way this works, to linearize this flow kick system, we need to linearize as we're moving down that trajectory. So the spatial derivative of that thing is what's happening. If we start close to that equilibrium, we're going to move down the trajectory, and what's happening to our neighbors? Are they getting closer to us, or are they moving further away from us as we move down the trajectory? And then it all jumps back and happens again. Jumps back under the kick. So this is the variational equation that is the tool that does that. And the way it works is it strings together all the linear systems. If you freeze time all the way down there, you can find the Jacobia, the linearizations at each frozen point all the way down that trajectory. And at each moment it's saying, are my neighbors moving towards me or away from me? And then you have to string them together to see what happens in the long run. Do the neighbors move ultimately towards, or do they do a bit of this and ultimately move away? So question. If all the way down that trajectory, that little piece of trajectory, if everywhere along there you've got frozen time attractors, will the resulting Flowkick equilibrium be attracting? If all the way down you've got frozen time attractors, does that mean that your neighbors have come closer to you by the end? And it's well known but counterintuitive that the answer to that is no. And the reason it's no is because you can string together reactive attractors. So it's the difference between asymptotic dynamics versus transient dynamics. So just this picture has this bullseye because the bullseye is showing you distance from the origin. And then the trajectories, while they're black, they're moving towards the origin, but while they're red, they're moving away from the origin before they turn around and come back. And you could line things up just right or just wrong, so that even though you've got frozen time attractors all the way down, you're always catching the reactivity that's moving out as you move down your system. So that's the reason that in a different branch of our work, we've focused on reactivity in two-dimensional linear systems. And so tomorrow's talk will be a much more, you could call it abstract, let's just look at this concept of reactivity in two-dimensional linear systems. And it's amazing to me that this is not already in the textbooks. What we do is decompose a system, a two-dimensional linear system, into radial and tangential coordinates, and those radial and tangential coordinates are so pretty. Each one is sinusoidal, and they're related to each other like sine and cosine, and there's a huge amount you can do with that fact. So tomorrow's talk will be about that. But for today, thank you very much for your attention.
Thank you so much for that talk. We do have a few minutes for questions. If you have a question, feel free to go to one of the mics, and Dr. Zeeman will address your question.
Thanks.
Hello, thank you for your
Hello.
talk. I was wondering if you're modeling a system as Flowkick, at what point would like some, I suppose you could say, environmental disturbance not be a kick? Like when I think about a kick, I may think of like a forest fire, so
Yeah.
like it resets the system, but depending on like at what point for how long that forest fire burns would it have to be modeled by something else?
So you're asking, I think you're asking a modeling question of when is it reasonable to call it a kick, a
Yeah.
discrete kick, and when should you give it, when should you not call it a discrete kick and think of it some other way?
Yeah.
I think that decision is probably made by what separation and timescales you have. So how long does you were asking about a forest fire, and were you asking about how long it burns? I'm sorry, that light is a little bit, means I can't see your face.
Yes.
Were you
yeah.
asking about how long it burns?
Yeah, precisely.
Yeah, so if it burns for a very short time compared to the time between the burns, then is it reasonable, it's a modeling decision to make, is it reasonable to say that very short time is essentially instantaneous compared to what we're studying, which is what happens between the burns? You could even, and that varies from system to system. So some systems, the reset, you described very accurately the burn as a reset. For some systems, winter is the reset. Like if a pond freezes, then winter can be a long time, but that's the reset. And it's when the pond thaws, and you're studying maybe amphibians or something, that's your starting point. So that entire winter freeze you could think of as an instantaneous kick. So I think it depends on the application, of course. Do you have one in mind?
No, I don't. I suppose I was just wondering whether like if it depends on the application, it's sort of like just like up to the person studying the system.
Yes.
So it's like a creative decision almost.
Yes, that's why it's wonderful to always work with domain scientists who understand the application. It's really fun be your mathematician self. It's interesting, you wear a bunch of different hats. So be your mathematician, abstract mathematician self. But I think when you're developing a model, it is so wonderful to have a colleague and friend who knows that system well, so they can tell you how reasonable your assumptions are, and they can help you understand whether considering it as instantaneous is well. They're always going to say no. They're always going to say no. Of course, it's not instantaneous. But as you discuss it together, you will understand whether it is a reasonable assumption to make, even though it's not perfectly accurate.
Right. Thank you.
Thank you.
We have another question.
So I was thinking of your harvesting example, and it occurred to me that as the population drops,
yes,
it's going to be hard to keep the amount of harvesting.
Absolutely.
So the kick is going to vary.
Absolutely. So you can play the same game or define the same kind of things with a multiplicative kick, where you're harvesting proportionally. Yeah. But even if you're harvesting proportionally, eventually there's going to be some level at which it just doesn't make sense to harvest. So like all models, it's insightful, but let's not drag it to its logical
so
extreme.
It's possible to is it possible to handle just the kick itself as a function varying in time?
Absolutely, yes. Yeah. And in fact, the forest fire, the savanna fire example of that Alana and Hoyleitzel and Sarah Iams looked at, the magnitude of the fire, so the kick is dependent on the amount of dried grasses on the floor. So that is a state-dependent kick, yes.
Good, thank you.
And of course, it's all possible. This theory won't apply to it all, but it's up to us to try those possibilities, right? Thank you.
Other questions?
Hello.
Hello.
So I was wondering, in your model for the disease,
Could you come a bit closer to the mic, please? Thanks.
Sorry, is this better?
Yeah, it's good.
Okay. So in one of your models for the disease, you went deep into the map and studied a portion and found that over 70% of the time it elicited a significant immune response. I was wondering if that's any sort of implication for underlying chaos in the system, possibly?
Yes, does it come from underlying chaos? I think it's, in this case, the underlying system, I don't believe the underlying system's chaotic. I believe it just has this multiple timescales and excitability. But it's not, excitability alone won't do it. We've been playing with that. And it's not, if you try it in a Van der Pol equation, that doesn't happen, just a two-dimensional excitable system. So, but I think it's the combination of excitability and multiple timescales that's doing it. Though surely a chaotic system is going to be an interesting one to study too. And I could be wrong, but I don't believe that system's chaotic.
Thank you.
It does have some very interesting bifurcations in it, but Hopf bifurcation things. Thank you.
Thank you
Good
again.
question.
I think we have time for one more question.
Oh, I really can't see you.
Hi.
Hello.
Yes, a little far back. So we have some early career people here. I'm wondering if you had any advice to share about doing interdisciplinary work.
About doing interdisciplinary work, yes. So as I started to say with this gentleman, that it really helps to, it takes time. It takes time to invest, you have to invest time to understand the discipline. You don't have to become, to do mathematical biology, for example, you don't have to become a biologist, but you do need familiarity with their language. So you really need to invest time, and especially for the application you care about, I think investing time to understand what their experiments can measure, what their words mean, letting go of the idea that we own the language. We don't even own the word linear. It's horrifying when you see what a biologist says is a linear thing. It's not what we think of as linear at all, but we don't own the language and we need to be open-minded. So building models with domain scientists is really exciting. You have to be prepared to be wrong in public. You talk to them about everything they want in the model, they think should be in the model, and then you go away, and you're a mathematician, you've got to simplify it. A model that reproduces reality is not useful. The useful model is one that extracts a very insightful piece of reality into a smaller, insightful piece of information that you can make predictions and try testing things with. Test different scenarios with. So you are going to be, as a mathematician, you're going to go away and simplify the system, and you're going to come back to your collaborator and say, look, I've got this great model, and they're going to say, you've thrown away all the important stuff. And so you need a friendship. You need what I call a friendship. You need to be able to talk to each other at that level and forgive each other for not understanding straight away. And accept that, oh yeah, you threw away something really important, let's bring it back in and start again. So I think those for me are fundamental. And so we've got to be prepared to be wrong in public. That was being wrong in public. We're very lucky, extremely lucky, that we're mathematicians. So even if we walk into another discipline with zero knowledge and we ask the most naive questions, even so, our collaborator is going to assume we're smart because we're mathematicians. It's a great gift that we have, and we are smart, and we're logical. But it's a gift that allows us to ask those naive questions and be a little less afraid of appearing, of being wrong in public. So that kind of courage, I would say, and the courage and finding nice people to work with, that takes you an awfully long way. And choosing an application you care about. It's so exciting, it's so motivating. If you care about it, you're not going to have trouble learning the language. That's my experience. Thank you.